welcome to the video lectures of Computer Architecture and Organization. I'm Priyanka from Ajay Kumar Garg Engineering College. Today I'm going to discuss the topic related to instruction cycles and subcycles, and then I'll be discussing the micro instructions as well. In the previous lecture, we have seen that this is the flowchart for the instruction cycle that we have if whenever we are executing any instruction. So the instruction actually execute in these phases, in these cycles, which could be divided into further subcycle. Now the instruction could be of multiple types. It could be a register type, it could be a memory based, or it could be an input output instruction. Right, so just see here, this is the flow chart which we have discussed in the previous section as well. So every time whenever we are starting with a new instruction, always the sequence counter is being cleared to 0, which says that we are executing the next instruction, and then the program counter would be storing the address of the next instruction. So from there we are going to pick up the address of the next instruction. So that is our next step. Then next is from that address we need to fetch the instruction. So we are from that memory of that address, we are storing that into instruction register. So that means we are getting the instruction from that memory address. And now after executing this instruction, we need to execute the instruction which is there in the next program counter. So suppose there is a sequential program. Currently we are executing the instruction which is at line 1. So address 1. Next time we need to execute the next instruction which would be at the next address. So for that we will be incrementing the program counter to 1. So that means next time we will be fetching the next instruction. So that's about the next instruction we have already done. Now from this IR, this is the instruction register we have. From this instruction register, we need to fetch out that what is the data on which we need to perform the operation and what kind of operation we need to perform. So we are going to do the task of decoding. So this task is decoding. Initially we were just fetching the instruction, now decoding. So for decoding, we are saying as we have discussed in the previous lecture, that the instruction register is of 16 bits, which is being divided into 3 parts. The 15th bit, that means the most significant bit, it is from 0 to 15. So the most significant bit is actually the I part, which is just specifying the direct or indirect bit. Alright, and then the 0 to 11, this is being used as the address of the operand, right? So we will be storing that into the IR. That IR 0 to 11 we will be storing into AR, so as to fetch the data from here. Now the operation would be specified in 12th to 14th bit. So here the instruction register 12 to 14 bit is the actual one which is telling us the operation. Now we'll be working on that to decide which operation is this. Now what we are doing is, we are saying D7. So D7 says that the 3 bits are 111, as because 7 is 111. So if it is 111, that means your 12th to 14th bit, these 3 bits are 111. So that says that this is D7. Otherwise, if it would be from D0 to D6. Now, if it is not D7, then it is a memory-based instruction. From D0 till D6, it's a memory-based instruction. Now, if it is D7, then in that case, it is not a memory-based instruction. It is either a register-based or it is an input-output instruction. Now, how we can identify that which type of instruction is this? So, after checking the D7, we'll be checking out the I bit. Now, this I bit will be telling us that whether this instruction is input-output or register-based. So, if I bit is 1, so it says that it is an input-output instruction. Now, if it is 0, it says it's a register reference instruction. So, from this we got to know that if you have D7 and then I bit value is 0, then it is your register reference instruction. Alright, so that's also mentioned here. Now, what if it is a memory reference instruction? In that case, D7 bit is 0, and then again you will check out the I bit. which is for checking out whether you're going to get the address directly or indirectly. So if the I bit value is 1, so it says indirect. If it is 0, it means it says direct. So directly you will get the address in this case. Otherwise, the address which you have is not going to have the data. It is again having an address. So you need to visit that address for getting the data. So this is what we have discussed in the last lecture. This is the complete instruction flow, instruction cycles. Now coming on to the register reference instruction. So here we are saying that this is the particular register reference instruction where, this is the register reference instruction. So what is the condition here? It should be D7, the value of D7 should be 1 and the value of I should be 0. So here we got that D7I dash, that's the condition for a register reference instruction. So here we can see that D7 and I bit value, D7 should be 1 and I should be 0. Now this says that this is a register reference instruction. Now here we can specify 12 instruction using 0 to 11 bits. So those 0 to 11 bits here would be specifying 1 out of the 12 possible instruction in case of register reference instruction. So we will see that. So from that we will identify that which operation we can apply. Now we are just transferring the content of AR during the time T2. This was the time when we were doing the transfer of AR to T2. Now at time T3, just see here, at time T3 we are finally executing the instruction after decoding, after finding out that what is the exact instruction. Okay, so here this is the condition that register reference instruction would be executing when the condition it's D7, that means here we have seen, then I dash, that means it's a register reference, and at time T3 we'll be going to perform this operation. So this is the condition. Now for the 0 to 11 bits, so these are total 12 bits and 0 to 11. So we'll be denoting that with BI. So BI is just denoting the bit corresponding to that address register, and by that bit we are going to judge that what kind of operation we are going to perform, right? So just see here, these are the possible in register reference instructions. So these are total 12, starting with RB0. Now what is this R? Just for the convenience, D7 I dash T3. This was the condition. This was the condition for the register reference instruction execution. So we are just renaming it as R. So this is our R. Now next is if B0. B0 says, that means your 0th bit out of 0 to 11 bit, 0th bit is 1. B1 says first bit is 1. B2 second bit is 1. So by this we can take this that what is the instruction. Now just see RB11, this says that clear accumulator, this is the instruction, right? And then RB10 is for clearing the E. E is just it's just a register storing could be storing the value of whenever we are doing the addition of two numbers. So we might need to store the carry out. So we store here in E. So to clear that we will be using this. Now RB9 is for CMA, which says that we will be complementing the accumulator. Whatever value is there in the accumulator, we will just complement it. Next at B8, it is complement the value of E. Then B7 is CIR, which is circular right. Right, so we know this is a shift operation. We need to shift all the bits to the right, and that too in circular fashion. We are going to discuss these circular in detail in micro operation topic. Then in B6 it is circular left. Then B5. B5 is for incrementing accumulator. So we'll just increment it. B4. RB4 is for SPA. This says skip if positive. So we are going to check out the value of the accumulator. If the 15th bit of the accumulator is 0, then we will just skip this instruction and will move to the next instruction. Next, our B3 is for skip if negative. So we are going to check out again the 15th bit of accumulator. If it is 1, so we will skip this instruction and we'll move to the next instruction. So PC is incremented. Now B2, it says SZA. It says skip if accumulator 0. So again we'll check out if the value of the accumulator is 0. We'll skip this instruction and we'll move to the next instruction. Next, skip if E0. Right, so that means we are going to check the value of E. If it is 0, then PC is being incremented. Now B0 is for halt. So we just want to halt the computer. So here we just got a list which says these are the possible instructions with register reference which will be identified with the bit number. So whichever bit out of this 0 to 11 would be 1, that would be telling us the exact operation. So this is register reference. Now similarly, the second category of instruction is memory reference instruction. Now for memory reference instruction, we said that the condition we have seen in the flowchart is that this is the memory reference. So that means D7 should not be 1, right? So that means your 12th to 14th bit should not be 1. That's a condition for memory reference. So here in memory reference instruction, we say that we'll be storing the, we'll be decoding the 12th to 14th bit of the instruction and storing it in D. If it is D7, then it is not a memory reference. Otherwise, that means from I0 to I6, it's a memory reference instruction. Okay, so here we will be again doing the operation at T3. Always the execution would be done at T3 and decoding was done at T2 time period. Alright, now we might need T4, T5 timing signals for the instruction execution depending on what the instruction is. Now just see here, on the basis of D0 to D7, D6, these are 7 operations of memory reference. In D0 we have AND, D1 add, then LDA, then STA, then BUN. Let's see it in detail. So here it's the detail that very first operation in the case of D0, when the value of 12th, 13th and 14th bit is 000, then you need to perform AND to accumulator, right? So it says at T4 time period, you will be actually taking out the value from the address register and storing that in data. So you have your one operand in DR now because you have taken the data from the address, memory, that memory address. Now you will be performing an AND of that data with the accumulator. So here for AND operation we need 2 operands. One is there in accumulator and another in DR. So we will be doing the AND and storing the final result in accumulator. Now whenever we are done with any instruction execution at the end, as because the instruction is finished, we need to clear the sequence counter to 0. So in every instruction you will see this is the last step, sequence counter is cleared to 0. Now coming on to the next add to accumulator. So this is the condition is D1. In case of D1 we need to perform this operation. So it says at D1 T4 what you are doing, you are again transferring the content of that memory address to DR. So you have your one data in data register and then you will be adding up the DR value to the accumulator and finally storing the result in accumulator. Now in this case, as we are doing the add operation, so we might have some carry out. So the carry out is being stored in E. So this is what we were discussing in the previous slide, that E is just to store the carry out. And then last sequence counter is cleared to 0. Then load to accumulator. You have your value data in your memory and you are just storing, you are just loading that data to accumulator. So just take that address, fetch the data, store it in DR, and then from DR we are loading that data to accumulator. So by this we have the data in the accumulator. Store accumulator, this says the data is there in the accumulator and you can take it out from there. So the content of the accumulator is being stored in the memory. So this is, you can see here, this is being done in 2 phases, 2 steps. This is being done in 1 time slot only. So depending on the operation. Now next is branch unconditionally. So this says that you, without checking any condition, you're just moving on to some other location. So that is there in AR. You have an instruction address in AR, and you're moving to, you need to execute that instruction. So we'll be taking out every time the instruction address from program counter. So we will just take that address and store to PC, and next time we will take the address of the PC. Next is BSA, branch and save return address. So this is in the case of when we are working with function. So currently we are working somewhere and we are calling a function, then we will come back to that point only. So here the currently you are on any instruction, the next instruction address is there in PC, but you are not going to execute that instruction. That will be executed later on. So the content of PC is you are storing in a memory address, which you have decided earlier that okay, on memory location 1 or memory location 0, I'll store the content. So this address, the address of the next instruction is stored in a memory location, and then that address is being incremented to 1, right? So here on this address you will find out the new address which you need to execute. So that is being transferred to PC. Alright, so suppose I am saying at 0 address I am storing the current program counter, and on 1 address I am taking that address and storing it to PC, right? So whenever I'll come back, I have to execute the address which is there at 0 address. So this is branch and save return address. Next, last is increment and skip F0. So what we are doing is, first we are taking the data from the address, storing it into DR, and then just apply the increment operation on that data. Now just check out whether this that you have that data with you. Now you will check out if that data is equals to 0, then you need to come to the next instruction. You are going to skip this instruction. So PC is being incremented to 1. So this is, first you take out the data in DR, just increment it. If you got 0, then you don't need to execute this instruction, you will move to the next instruction. So these are 6 types of memory reference instructions. This is just a flow chart for showing all the operations in detail, that at T4 it is going to do this, at T5 it is going to do this, the same one. Now coming on to third type of instruction, which is input output instructions. So input output instruction is just that we need to take some input from the input device, or we need to give some output to the output device. So that kind of stuff we are going to do here. Now again, let's see the flow chart here. For input output, we are saying that D7 should be 1, and here this is the input, that means the value of I bit should be 1. So the condition for input output says that it should be D7, I and T3. So D7 1, I 1, and at time T3 you are going to execute the input output instruction. Now for convenience, as like in register we have renamed it as R, here we would be renaming it as P. So this is a P, which is a condition for input output. Now now we have to find out what kind of input and output operation we need to perform. So again, as like in register, we have taken the bits from 0 to 11 of the instruction register. Here, as because we don't have much of the input output instructions, so we don't need 0 to 11 bits, only 6 to 11 bit would be enough. So we are not going to consider the 0 to 5 bits, we are only going to consider the 6th to 11th bit of instruction register. Now that bit will be used to identify what kind of input output operation we want to perform. Again, that will be taken as the BI, just to find out that which bit is 1. Okay, so when we are done with the operation, we will be clearing the sequence counter to 1. So let's see the instructions, the input output instruction. Before understanding that, what happens exactly, the input output configuration, how does it work? This is the input device keyboard. So we have entered a key, and that is being, through the transmitter interface, that is being stored in the INPR, that is an input register. So whatever input we are giving from any input device will be stored first in INPR. and from there it is being stored in the accumulator. So you can see here, from there we will be storing it to accumulator. Okay, so this is the input task. Now in case of output, we have some data in memory, or we have processed some data and we need to show it to the output device. So we will be saying that we have the data in accumulator, and from accumulator we will be showing it to the output device. So from accumulator it will first go to the output register, right, and then through the interface it will go to the output device. So this is how the input and output configuration work. We need an input output device, then we need an interface, and then we need a register for storing the intermediate data. Okay, so we got to know INP instruction. So in case of input and output, we just need 8 bits. We don't need 16 bits. We just need 8 bits. So we can see the 8 low order bits of accumulator, right? So that data is being taken from the INPR. When the data is there in input, so from INPR register we will be transferring it to accumulator. That's the input instruction. In case of output instruction, the least significant 8 bits of accumulator is being transferred to the output register. So this is how these two instructions work. Now here are the possible input output instruction. So P is, again, as I said, it is denoting D7IT3, which says this is the condition for input output instruction. Now B says that B11 means 11th bit is 1, B10 means 10th bit is 1. So in case of B11, we will be performing the input operation, right? So we will be taking the input character from the input device and we will be storing it to accumulator. So just see here, the content of the input register would be transferred to the accumulator 0 to 7th bit. And then after transferring this content, as because we have taken the content from input register, now the input register is ready to store another data. So for that we will be using a flag. So flag for input is being cleared to 0. That means now the input register is ready to take another content. Similarly, B10 is for output. So when your 10th bit is 1, so that means you can do the process of output. In that case, you have your data in accumulator and you will store that data, that 0 to 7th bit of the accumulator, in the output register, and from output register it will go to the output terminal, and then it is now you're clearing it to 0, flag is being cleared to 0. Now the other instructions are SKI, which says skip an input flag, right? When you just wanted to skip the input flag, so if your flag is 1, then you're incrementing your PC to 1, that means you're clear, you don't want to execute this instruction, you're moving to next instruction. Now SKO, it says skip if an output flag is there. If the output flag value is 1, then in that case you will be incrementing PC to 1 just to point to the next instruction. ION, this is for interrupt enable on, right? So we'll talk about the interrupts as well. Interrupts enable, we are just enabling it. Then IOF, that means we are disabling the interrupt flag. Okay, so these are the instruction. Now as we have seen that these two are having important role, FGI and FGO. So FGI is flag for input and FGO is flag for output. Okay, so that's about the input output instructions. Now coming on to the next is programmed interrupt. Now what is programmed interrupt? Now we are saying that a computer needs to execute the instruction. The processor is involved in every instruction. Whenever I am working with an input or output device, as I am clicking any key on the keyboard, it takes some time, right? Because human speed is very less as compared to the computer speed, processor speed. So the time which a human is taking to press any key, to give input to the keyboard from the keyboard is taking a lot of time. When I am done with the input, the processor needs to take that data and store it into the accumulator, and then further it will be storing it to the memory. Now for this process, processor is involved. Now a processor needs to every time check whether there is a data available in input output register or not. So it takes time that processor every time needs to come and check that whether there is a data or not. So it is actually we are wasting processor's time just every time processor needs to check. So let's understand this with example. Now what we are saying, suppose we have a processor and for executing any instruction in an instruction cycle, the processor is supposed just taking 1 microsecond, right? So this is the speed of the processor. But if we talk about any input output device, and on average if we say, suppose the maximum characters which a human can give is 10 character per second. That's the speed for the input device. And now these 10 characters per second is exactly, it means 1 lakh microsecond it will take, right? So 1 lakh, after 1 lakh microsecond we will have data, and the computer needs 2 instructions to check out whether there is a data in INPR or not. So that says that every time this processor needs to waste 50,000 times. 50,000 times a processor needs to check whether there is a data or not. So it's just we are wasting the CPU, we are wasting the processor capability. Rather than that, we can use it for executing some other instruction. Now how the processor will get to know if the processor is not going to check out? So here we have a feature that we will interrupt it, right? As like we are speaking and someone wants to ask a question from me, so you can interrupt me in between. Similarly, processor is executing some other instruction and input or output wants the services of the processor will actually interrupt the processor, and processor will get to know that okay, input needs me for some processing. So the processor will stop that current task, will come to input, will execute its instruction, and again will go back. So the processor need not to waste time for just checking out whether there is a data for handling in case of input and output. That's what we call the interrupt. So here there is a term called program interrupt. So here let's see the flowchart of the interrupt. So here what we are doing is, just let's understand from here, we are going to fetch an instruction and we'll decode it, and then if suppose there is not any interrupt, so we will just execute the instruction normally. But if suppose we have IEN is a flag for just interrupt enabling. If the processor is actually working on some high priority task and does not want to be interrupted, so in that case IEN is being set to 0. So IEN is 0, that means it will process the normal instruction. There is no interrupt, right? As because the processor don't want to get interrupted. If the value of IEN is 1, that means the processor is ready to be interrupted, and if there is any any task of input and output, so input and output can interrupt the processor. Then after checking IEN flag, we are going to check out FGI. So this is for the input flag, and FGO is for output flag. If FGI flag is 0, that means input does not want the services, is not interrupting. Then in that case, in case of 0, we are going to check out output. Whether it is also 0, okay. So IEN 0, FGI 0, FGO 0, in all these cases, we are just going to process the instruction normally. There is no change, there is no interrupt. But what if, suppose we have here in this case, IEN is 1 and either of FGI or FGO is 1. Then in that case there is an interrupt. Processor is ready to accept interrupt, and out of input or output there is any interrupt by any input or output device, then in that case we are setting up a variable R to 1, which says there is an interrupt. So here just see, when the value of R is 1, so that is there is an interrupt. That's not a normal instruction, there is an interrupt. And in that case, how you are going to handle that interrupt? So first, what you are going to do is, you don't need, processor was executing some sequential task. Processor does not need to execute the next instruction, as because processor needs to execute the input and output instruction. So the address of program counter, the next program counter is carrying the next address. So the next instruction address is there in program counter. We are storing that address to memory location 0. We have just decided it earlier that this is the logic we will always do, that we will store the next instruction address to memory 0. And then the input and output instruction we are storing in one address. So from the address location 1, we will take that address and store it in program counter. And then program counter will execute it. After doing that, we are just doing this. That means we have executed this. This interrupt has already been handled. So currently the CPU is executing. So the CPU cannot execute any other. So we are just setting IEN to 0, so that any other instruction will not interrupt meanwhile. So IEN is set to 0 and R is set to 0. So these two flags are being set to 0. So this is how the interrupt works. Okay. Now just again see that how it is working. Again we will say that if IEN is 0, that means interrupt is the CPU does not want to be interrupted. So in that case the normal instruction will be executed. If IEN is 1, in that case these two flags are being checked. If any of these flags is being 1, so we will take out that instruction and will execute it. So this is what explained here. Now exactly see how the interrupt works. So this is the best diagram to understand that. Now just see, this is the main program which the computer, the processor was executing, and currently the processor is executing the address 255, and next instruction which processor needs to execute is 256, and at 255 it got an interrupt. So 256 instruction will not get executed. We will store this 256 at memory 0 address. So just see here, at memory 0 address we are storing 256. That means whenever interrupt will get handled, the processor will start by this address. After that, from where we will get the instruction for input output which needs to be handled, it's stored in PC, it's stored in address 1. So from the address 1, we'll take that instruction address and store it to PC, and this says the instruction is branch unconditionally to 1120. So we will go here at 1120 address. Here there is an input output program. We will execute it, and when it is done, it is just doing again branch unconditionally to 0. So just see here, from here we have shifted here. It is being handled input output. After that, the processor again needs to handle the same 256 instruction. So the branch unconditionally will move to this, which will actually come here. So this is how the instruction in case of interrupt will work. Okay, so this is again the same way we have seen when we have an interrupt. So that is the R. At time t0, we are storing the the 0 address value to AR, right? And then PC to TR. It's just a temporary register we are taking, and then that TR will be stored in AR at time t1 and PC to 0. So this will move PC to 0, right? And then PC is being incremented, right? As because at address 1 we will get the input output instruction, and then just set the IENR and SC to 0. So this is the exact instructions, micro operations being executed in case of interrupt cycle. Okay, now let's just combine a normal instruction with an interrupt, and this is the combined flow chart. We have already seen this part. We have already seen that we have not considered this R. We have a normal instruction. We are not considering interrupt if. So at time t0, we are just going to fetch the instruction, then we'll decode it, then we'll find out on the basis of D7 that whether it is an input-output or memory reference or register. So if D7 is 1, then it is either an input-output or register. If it is D7 is 0, then it is either direct or indirect memory address. So we have seen this. Now just merging this part as well in the complete flowchart, this says we are going to check out the value of R. If R is 0, then it's a normal instruction. If R is 1, then it is an interrupt. So this part is for the interrupt. If it is an input-output instruction interrupt, so processor needs to handle that. So that part is being shown. Okay, that's it about this lecture. Thank you for watching this video.